Astronaut Rick Hauk joined NASA in 1978 in preparation for the Space Shuttle program. Hauk served on the support crew for the first two missions and then piloted Challenger in 1983. He flew into space again aboard Discovery, one of the 3 Space Shuttle orbiters. Following the Challenger disaster of 1985, Hauk flew the next shuttle mission into space. This was the 26th Space Shuttle mission and America's return to space.
Hi, I'm Rick Hauk. Are you afraid of heights? Many of our astronauts have stood on the edge of the space shuttle hundreds of miles from Earth. If you get dizzy looking down from a mountain or a building, think about looking out into the endless black of space. Below you glows a beautiful blue Earth, and all you hear is yourself breathing inside the spacesuit. As one astronaut said, it's like being on the world's highest diving board. The film you're about to see has some spectacular footage of spacewalks around the shuttle. It looks like the astronauts are floating calmly, but they're actually moving at over 17,000 miles per hour. You'll see spectacular views of our Earth, as well as shots of the astronauts wrestling with the giant Intelsat satellite. The Endeavour Intelsat repair mission highlighted the versatility of the space shuttle and astronauts in space. Watch this exciting rescue mission. It teaches everyone that teamwork is the best way to win. And when America's top astronauts, engineers, and scientists work together, adversity leads to discovery and success.
From the beginning, STS-49 would stand out as an extraordinary mission. As Endeavour rolled onto the tarmac in Palmdale, California on April 25, 1991, it set the stage for America's 47th Space Shuttle mission. Endeavour was a milestone, bringing the shuttle fleet back to full strength after the loss of the Space Shuttle Challenger, signifying a new level of confidence and ambition for the American space program. But the maiden voyage of Endeavour would prove to be not only a test of the space transportation system, but a test of the entire space flight program. After more than a year of intensive training, the crew of Endeavour was ready to face the complex inaugural voyage ahead. Navy Captain Dan Brandenstein commanded the crew of 7, while Air Force Lieutenant Colonel Kevin Chilton served as pilot. The piloting skills of both men would be crucial to the success of the mission. The remaining members of the crew, mission specialists Richard Heeb, Dr. Catherine Thornton, Coast Guard Commander Bruce Melnick, Air Force Lieutenant Colonel Tom Akers, and Navy Commander Pierre Thuot shared in the responsibility of achieving the mission objectives. The primary objective, the retrieval, repair, and reboost of the International Telecommunications Satellite, or Intelsat 6 F3. A wiring error on the unmanned commercial booster rocket marooned the satellite in a useless low orbit after its launch in 1990. Intelsat commissioned NASA to rescue the stranded satellite. Though this was not NASA's first satellite rescue, it would be one of the most challenging for the Space Shuttle program. Endeavour and her crew would engage in the first attachment of a solid rocket motor in orbit, and the first attempt to perform 3 consecutive spacewalks. Another objective of the flight would be the assembly of station by EVA methods experiment, or ASEM. The mission specialist teams of Akers, Thornton, Thuot, and Heeb would perform EVAs, or spacewalks, to evaluate equipment and techniques for the construction of Space Station Freedom. In the payload bay, the astronauts would build a truss structure and evaluate EVA operations to be used for space station assembly. To achieve these objectives, the crew of Endeavour underwent months of rigorous training at NASA's Johnson Space Center in Houston, Texas. At the Precision Air Bearing Facility, a mock-up of Intelsat 6 was used to assess how the satellite would respond in space and to demonstrate the capabilities of the unique capture bar.
Okay, one more time at half. Why don't you guys put a little wobble in it, if you can.
Thuot would use the capture bar to catch the satellite and stop its rotation. The bar included a grapple fixture for the robot arm to grab the satellite and place it on top of the solid rocket motor.
Okay, that's better.
Thuot and Heeb continued their training in the Weightless Environment Training Facility. This training focused on the task of attaching the satellite to the solid rocket motor and preparing it for its launch from the shuttle cargo bay. It would pay off handsomely in space. The complex dynamics and interactions of satellite, shuttle, robot arm, and astronaut were difficult, if not impossible, to recreate on the ground, and proved to be the most serious challenge facing the satellite rescue mission. May 7th, 1992, a relaxed and confident Endeavour crew heads for the launch pad. Weather problems persisted throughout the day, but the rainy skies couldn't dampen the spirits of the 7-member crew.
Lock your visors and initiate O2 flow. Good luck on the maiden voyage of the newest shuttle Endeavour.
T-minus 10. We have a go for engine start. 6, 5, 4, 3, 2, 1. Booster ignition and liftoff of the maiden voyage of Endeavour on a satellite rescue mission.
Roll program, Houston. Roger, roll, Endeavour.
SRB separation confirmed.
Following a flawless liftoff and ascent, Endeavour settled into orbit. Over the next 2 days, Endeavour and the stranded satellite circled the Earth while performing a series of crucial maneuvers as a prelude to the rendezvous. The success of this unique mission would require an unprecedented level of coordination between the Intelsat control facility in Washington, D.C. and mission control in Houston. An intricate dance ensued as the flight crew gradually raised Endeavour's altitude and Intelsat controllers lowered their spacecraft.
This is a 45-second burn of the twin orbital maneuvering system engines that produce about 6,000 pounds of thrust, raising Endeavour's low-ends orbit from 146 to 187 nautical miles, getting it closer to a more circular orbit as it continues its chase to catch up with the Intelsat spacecraft.
As the countdown to the first spacewalk proceeded, crew members began the checkout of the robot arm and spacesuits.
And Houston, as you gathered, we've completed equipment prep, and as you can see, it's just as crowded as we expected it to be.
And we copy, Pierre. Thanks.
On Sunday, the 4th day into Endeavour's mission, Thuot and Heeb stepped into the payload bay to begin the first rescue attempt. While Thuot grappled the satellite, Heeb, from his unique vantage point in the payload bay, served as an extra pair of eyes for the cockpit. Melnick operated the robot arm from inside the orbiter.
Okay, you ready to go for it? Okay, go for it. Hey, Pierre, here we go.
Unfortunately, the cards were stacked against the crew this day.
In a little bit, Bruce. Coming in. Oops, I missed it. Hang on. Okay, have to catch it next time. Okay, we got a rate on it now.
The capture attempts caused the 4.5-ton satellite to wobble so much it became impossible for Thuot to attach the capture bar. Endeavour was forced to back away to avoid a collision with the satellite.
Verify the shower cap pedals that we flipped up are
Dan,
secured.
Rendezvous and Fidos are working on
Okay.
a best maneuver for you to back out here so we can stabilize for about 6-8 hours. We'll try to come in again tomorrow.
Okay, that sounds good. We got a slight opening rate, and we're comfortable right here.
Okay, sounds good. We'll have some words for you shortly.
Rotation rate on the arm. This was a full pitch deflection. Trying to...
After analyzing the downlink footage from Endeavour's cameras, the crew held a conference with Mission Control to discuss conditions contributing to the unsuccessful attempt. Prime factors included the satellite's unexpected sensitivity to touch, the unanticipated movement affecting Thuot's positioning on the robot arm, and reduced visibility on the dark side of the Earth. The next step was clear. A second attempt would be made on Monday.
Probably the most important question first, and that's where was the...
Engineers on Earth struggled throughout the day and into the night to come up with a better way of capturing the satellite. Monday, May 11th. Thuot and Heeb stepped from the airlock into the payload bay. While Mission Control had brainstormed for the second EVA, the crew had come up with a few suggestions of their own. They would attempt the capture in maximum sunlight to give Thuot the best view. Time would be allowed for a bump test, bumping the capture bar against the left side of the cargo bay to familiarize Thuot with the dynamics. This would also determine how the bar would respond when striking the satellite in a weightless environment. Perhaps most importantly, Brandenstein would have to keep Endeavour in position beneath Intelsat for as long as it took Thuot to get into optimum position.
Awaiting good sun angles now to begin maneuvering Pierre Thuot on the end of the robot arm into the tail end of the satellite.
Yet, despite the planning and coordination between ground and space, this second attempt also failed.
Fire. I do believe. On. Good. Oh, not. Oh, no. Back away. Uh-oh. God, surely you had it.
During the 5.5-hour spacewalk, Thuot made 5 attempts to attach the capture bar to the satellite.
Yeah, you were right in there. Yeah. On the left beam end, I could see clearly.
That was right. That was when I was looking at it. I can't see the left one because it's hidden by the bar, but...
Yeah, I saw the left one.
It almost looked like you stopped the rotation. I think you did some. You stopped the rotation. It wasn't enough to fire the latches.
Yes, that's true.
Problems arose when the trigger release on the grapple bar failed to snap into place due to the delicate equilibrium of the orbiting satellite.
So let's go in. The right thumb and down. Go in. Hold it right there. Dang it. Why it's not grabbing? I didn't get it. It might be all of it today.
The situation was becoming increasingly frustrating. After the second attempt, Thuot noted a wide margin of difference between performing the capture in NASA's microgravity simulators and actually trying it in space. Because of Brandenstein's piloting skills and frugal use of fuel on the second attempt, enough fuel remained for one more rendezvous.
And Dan, we've been looking at the prop. Just want to tell you that your formation flying there has been outstanding. We've had practically no forward prop usage at all. Fine job you're doing.
A third attempt was immediately approved, but a replanning of strategy was clearly necessary.
All right, Endeavour Houston, with kind of the big pictures, we're planning on an 8-hour sleep period, no EVA for tomorrow. We're going to rendezvous with Intelsat on day 7.
These guys grab it, stabilize it, de-spin.
Human intelligence was Endeavour's strongest ally, and ingenuity and adaptability were crucial to success. The hours that followed were a maze of brainstorming sessions and hands-on tests. For veterans of the space program, the level of activity was reminiscent of the early days of Gemini and Apollo. The Tiger team, a group of troubleshooting specialists, discussed the options available.
But we got 1 day left, 1 attempt left. Where do you want to put all your eggs?
Among the ideas suggested, a revised 2-man spacewalk to capture and repair the satellite. Engineers also discussed using the orbiter's robot arm to maneuver a crew member to the top of the satellite and capture it from there. Meanwhile, the crew came up with a simple yet revolutionary plan, a record-setting 3-man spacewalk, a first in the history of the space program. The crew downlinked a sketch photographed on the electronic still camera developed by Johnson Space Center to demonstrate their plan to mission control. 3 astronauts, Thuot, Heeb, and Akers, would attempt to capture the satellite by hand.
You've got the capture bar. Regardless of the orientation, our big thing right now is this may not be clean. You know, this is not, I mean, it doesn't even have to be pretty. We just have to get this thing, but it has to be safe.
Safety was a primary concern. Piloting had to be exact to ensure there would be no risk of a collision between the satellite and the orbiter. Every possible danger was assessed.
So the 3 crew members will be putting on their suits and climbing into the airlock along with all of their tools and equipment that will be necessary for tomorrow's spacewalk attempt to capture the Intelsat spacecraft.
In addition, there was some concern as to whether the 3 astronauts could fit into the airlock. So, before the plan was approved, it was tested in the orbiter and on the ground. Dozens of engineers, astronauts, and other specialists debated and tested the plan by using mock-ups of Intelsat in the underwater tank with astronauts Story Musgrave, Rich Clifford, and Jim Voss. Similar mock-up demonstrations were conducted on the air-bearing table.
Okay, we just came out of the mission management meeting and presented the plan, and I think we've got something that is going to pull together here.
The go-ahead was given Tuesday night. The third and final attempt would be made the following day.
Covered as many of the bases as we could today.
Good evening, friends. A high drama is being played out in space right now.
A risky rescue attempt, an unprecedented mission.
While the astronauts worked 225 miles above the Earth, Americans kept an ear to their radios and an eye on their televisions for the latest news.
About 4 minutes ago, the crew of Endeavour.
Good evening. The drama
and many were eagerly offering their own suggestions on how to capture the stranded satellite. Velcro, fishing hooks, and lassos were some of the methods suggested.
The riskiest.
Wednesday, May 13th, Brandenstein and Chilton began maneuvering the orbiter closer to the satellite. 12 miles behind the satellite, as they approached the most critical burn of the rendezvous, they discovered a previously unencountered glitch in Endeavour's computers. At the same time, a thunderstorm over a ground communications site caused the crew to lose contact with mission control. The computer problem on board Endeavour meant Brandenstein and Chilton would not be able to compute the final critical rendezvous burns. Ground control studied the problem with only minutes to decide to continue the rendezvous or delay for one orbit. Another option was to skip today's attempt and study the problem for another day.
I'm going to do. If we can get some confidence back in the solutions, what I'm looking for is something that'll bail me out for loss of comp. Otherwise, I'm going to burn ground.
Or should they try it without the onboard computer and attempt a ground-controlled approach to the satellite? This type of approach meant that data normally collected by the shuttle's computer would need to be calculated on the ground and relayed up to the crew. With only 45 seconds until the burn, Endeavour regained communications with Houston. The decision was to delay. Heeb, Thuot, and Akers were already in the airlock and waited another hour and a half in their cramped quarters. Precious fuel had been used to execute the delay maneuver. Now, more than ever, Brandenstein must fly a perfect final approach. He accomplishes this with fuel to spare. An anxious nation held its breath as Thuot, Heeb, and Akers left the airlock.
Out in the payload bay, 3 spacewalking astronauts are preparing to install the bottom plane of the assembly of station by EVA methods hardware.
After building a bridge structure across the payload bay using struts from the space station test and portable foot restraints, the trio positioned themselves for the capture. Heeb on the edge of the payload bay, and Akers on the strut spanning the payload bay. Thuot, on the robot arm, adjusted his movements in coordination with the satellite. Meanwhile, Brandenstein positioned the crew at eye level with the underside of the satellite. In this attempt, every detail had to be exact.
With the coding, it may just come right back to Tom. Over.
It may. I guess all we can do is kind of sit here and wait for the right opportunity. And
I haven't got anything else on my dance card. Over.
Yeah, real easy, guys. Real easy.
Don't bring us any closer, Dan.
Okay, I'm stopping it.
I'm afraid it's going to rise out of my reach, but we'll see. Over.
And, as the saying goes, the third time was a charm.
I can get it.
Can you get yours, Tom?
I can get mine.
Okay. Wait. Let's do it.
Got it. All got a good grip?
Yes, sir.
Houston, I think we got a satellite.
Yeah, we're watching down here. We got a lot of smiles down here, Dan.
It ain't over yet.
Indeed, it wasn't over yet. But with the most difficult part of the mission behind them, things could now proceed as planned. After rotating the massive satellite, Thuot and Heeb attached the capture bar. Once in place, Melnick maneuvered Thuot under the satellite to tighten the bar. To do this, Melnick had to move the robot arm, with Thuot still attached, extremely close to the orbiter and truss structure. This unexpected task was not part of the pre-mission training. Once Melnick used the robot arm to lower the satellite into the cargo bay, a new booster rocket was secured. When it was all over, another record had been set for the longest spacewalk in the history of the space program, 8 hours and 29 minutes. With the crew safely inside the airlock again, the satellite was ready for deployment.
There's a delay, don't worry.
Yeah.
There's a delay.
There's a delay?
Yeah.
How much?
However, the onboard wiring configurations on the new orbiter were different than anticipated by the ground staff, so some minor readjustments were required by ground support.
Primary deploy A arm on, talkback gray. Stand by for fire. 3, 2, 1, fire. Astonished.
Hey, that old boy didn't want to go, did he?
After 2 attempts to deploy, ground controllers sorted out the wiring change, communicated the correct switch positions to the orbiter, and Intelsat 6 was on its way to its intended orbit of 22,300 miles. But Endeavour's work was yet to be completed. Mission managers decided to extend the mission an extra day, allowing for a 4th spacewalk on Thursday to practice the space station assembly techniques. The crew had originally planned 2 days for these spacewalks. But since the space station test structure had been partially built for the satellite rescue attempt, they were able to incorporate most of the activities of 2 days into 1.
And just so you know, the game plan for the day, it's another day, another EVA.
That's the type of game plan we like.
On Thursday, the attention of the crew and the nation was again on the payload bay. With the 4th and final EVA of Tom Akers and Kathy Thornton, the crew of Endeavour set the record for the most spacewalks in NASA's history. The pair spent 7 hours and 45 minutes demonstrating techniques to be used during space station construction and maintenance. However, this spacewalk was not without its complications. When the crew members used foot restraints to control their body positioning, the time required to accomplish a task in space was very close to the time required in the water tank. But free-floating exercises proved much more difficult and time-consuming. Mission planners will use the lessons learned during the 4 spacewalks to increase the efficiency, training, and techniques to be used in the assembly of Space Station Freedom.
As the son of a sailor, I went out on the sea for adventure, expanding the view of the captain and crew like a man.
Endeavour Houston, good morning. The SDS-49 trainers send Dan and his spacefaring crew their best for making the maiden voyage of Endeavour a spectacular success. They wish you well as you start preparing to come home to port.
Well, good morning, Houston, and thank our training team of those fine words. We couldn't have done it without them getting us squared away before we left.
Endeavour and its crew sailed into the 9th day of the mission, preparing the orbiter systems for the trip home the next day. It was a day for reflection as the crew held a news conference from the orbiter.
We were speculating how many people were involved. We knew it was a lot, but we didn't have a clue how many it was. And they did a fantastic job. There was, we had some ideas, they had some ideas, we shared them. They had a lot of data we didn't, and went off and worked it and came up and fine-tuned some of our ideas with theirs, and you saw the end result. It just proves that NASA has a great team and can really do the job when the chips are down.
With the mission objectives behind them, the crew prepared the orbiter for re-entry.
Endeavour Houston, you have a go for the deorbit burn.
All right, Houston, go for deorbit burn.
But before putting this mission in the books, Endeavour had one more test. After touchdown at Edwards Air Force Base in California, a drag chute was deployed from the back of the orbiter. Engineers designed the chute to improve braking and steering control during landings. Long after Endeavour has been rolled off the runway in preparation for another mission, planners and engineers will use the information and knowledge gained on this flight to improve future flights. In hindsight, most agree the reasons for mission success were clear. Despite the problems often associated with a maiden voyage, Endeavour performed flawlessly.
We felt pretty good about the mission. It had been real interesting and challenging, and we're real happy with the way Endeavour performed. It performed like a real champ, which is phenomenal for the first flight of a new vehicle.
Perhaps the simplest explanation for this mission's success is the team effort, the ability to adapt and learn in the face of adversity, demonstrated by both the crew and ground staff. Proof that people are a vital link in the American space program, now and into the 21st century.
Astronaut Rusty Schweickart joined NASA in 1963. He piloted Apollo 9, logging over 241 hours in space. Schweickart tested the life support packs used on the moon during a 46-minute spacewalk. He was backup commander of the first Skylab mission. Schweickart was then named Director of User Affairs at the NASA headquarters. He was responsible for transferring the discoveries in space into applicable uses for science and commerce.
Hi, I'm Rusty Schweickart, Apollo 9 astronaut. Have you ever considered life on another planet or life in another galaxy? Can there be life elsewhere in the universe? We humans here on Earth are so engulfed in our own problems that we can't imagine a universe teeming with life. And yet, the universe is so unimaginably large that it seems arrogant to imagine that we're the sole outpost of life in the cosmos. What is the universe? How many stars and galaxies are there? Thanks to NASA and America's continued space program, we've learned there may be more to life than just the Earth. The film you're about to see is a special look at this biggest picture of them all, the universe. It goes beyond the Earth, beyond our solar system, even beyond our own Milky Way galaxy, into the vast, dim reaches of the cosmos. This seeming infinite space is populated by clouds of gas and dust, red giants and white dwarfs, neutron stars, pulsars, and black holes. These cosmic characters are gathered into galaxies, clusters of galaxies, and superclusters. And while the time scale is enormous compared with normal human time, the entire universe is evolving and developing. Some of the billions of stars in these billions of galaxies have planets around them, perhaps most of them. Is there life on these other planets? Will we ever know? Join me in watching and wondering about this most fundamental question humankind has ever asked as we watch this briefing on the universe.
The study of the universe spans almost inconceivable extremes of size and distance and time. From the vast island of stars we call a galaxy, to the tiny atom and the particles that comprise it. From cosmic events that occurred billions of years in the past, to microcosmic events in the present that endure for only billionths of a second. To explore the universe at these extremes, the scientist builds instruments that extend his reach and his vision. His great telescopic eye has the light-gathering power of 1 million human eyes. It peers not only into the depths of space, but far back in time. Since the light it now observes may have left its source when dinosaurs inhabited the Earth. His telescopic ear is tuned to the invisible radio sky. It detects not objects, but the radio regions associated with them, and at distances far beyond the range of the largest optical telescope. But the radio waves and the visible light that pass through the Earth's atmosphere to these ground-based telescopes are only part of a broad spectrum of radiation, most of which is blocked by the atmosphere. So electronic instruments are lifted above this murky and turbulent layer. Airborne by rockets, by balloons, in unmanned astronomical observatories, in manned laboratories, and in spacecraft orbiting the planets. Instruments probe the near and distant environments of space and open new windows on the universe. In the beginning, it is believed, all the matter of the universe was contained in a primordial atom, an unimaginable concentration of elementary particles. In one gigantic detonation, the contents of this cosmic fireball were hurled outward in all directions. After 1,000,000 years of expansion, the universe was an intense blaze of light. Then the radiation cooled. And after hundreds of millions of years, great clouds of hydrogen gas began contracting and, in time, evolved into the galaxies we now observe. Inside these galactic whirlpools, smaller fields of gravity condense hydrogen into stars. Stars are inconceivably hot. So hot, they sustain thermonuclear reactions that transform hydrogen into heavier elements. Sometimes their hydrogen fuel burns so fast, they flare out in violent explosions, hurling new elements across space. Like a great wind, the radiant energy of starlight drives these clouds of dust and gas throughout the galaxy. Out of these clouds evolve new generations of stars. More than half the stars in our galaxy travel in groups of 2 or more, orbiting around a common center of gravity. Like galactic comets, immense clusters of stars swing in and out of the galaxy in vast, eccentric paths. Some small stars do not travel in the company of other stars. Our own sun is one of these. To the astronomer, the sun is a vast laboratory for the detailed study of a star's structure and energy. The vertical tower of the solar observatory supports a heliostat mirror which tracks the sun, gathers its rays, and reflects them down a light shaft that extends 300 feet below ground. At the end of the shaft, the rays are cast back to an observing room where minute-by-minute changes across the face of the sun are observed. Another mirror projects a light beam to a spectroscope, an instrument which splits the light into its component colors, a visible spectrum. The dark lines that cut across the spectrum band are produced by the radiation from the sun's interior shining through its atmosphere. Each line is the signature of a chemical element such as sodium, iron, calcium. It is this array of lines that forms the code which describes the properties and motion of a star. By narrowing the view of the sun to a single line of the spectrum, each level of the solar atmosphere can be photographed, and each reveals a remarkably different aspect. And with the addition of computer mapping and color processing that distinguishes levels of brightness, a detailed and multidimensional picture is obtained of a sun undergoing dramatic and turbulent change. The sun is a sphere of hot, seething gases and surges of radiation. Most of the light we get from the sun comes from the thin, bright layer which defines its visible edge, the photosphere. Above it, the chromosphere, a region of flaming outbursts of gas, extends through a transition zone to the thin outer atmosphere of the corona. Once thought to be a quiet layer of the solar atmosphere, the corona is now revealed to be a region of dramatic large-scale changes and unexpected turbulence, with temperatures reaching millions of degrees. Deep beneath the sun's atmospheric shell is the core, a violent nuclear furnace. Here, hydrogen is fused into helium, and in the process, some of the matter is converted into an enormous amount of energy. Radiating outward as a gas, it convects like a boiling liquid beneath the surface. The turbulent, bubbling motion is visible in the granular cells of the photosphere. Sunspots, regions of intense magnetic fields, appear on the surface, disappear in a few hours, or grow and persist for months in a mysterious 11-year cycle. The sun rotates once in 27 days. Because its equatorial regions rotate faster than the polar caps, the shearing action in the gas contorts the magnetic field into tangled structures which give rise to the sun's eruptive action. Shaped by these magnetic fields are the spectacular prominences, titanic streamers of gas reaching heights of more than 500,000 miles above the surface. The greatest explosions in the solar system are flares, intense bursts of light erupting with the force of billions of hydrogen bombs. They move at hundreds of miles a second. Then, after minutes or hours, they fade away. The dark areas across the solar disk are coronal holes, which may provide new clues to the sun's interior, and may be a source of the solar wind that blows outward to the farthest planets. On Earth, effects of these solar events are visible when auroras light up the dark Arctic sky and radio communication is disrupted. The sun is an average, middle-aged star. Yet it will generate heat and light for billions of years to come, as it has for 5 billion years past. It dominates the motions of all bodies in the solar system. Nearest the sun and obscured by its intense glare is Mercury, a cratered planet much like our moon. Temperatures rise to 800 degrees, but no clouds or atmosphere protect its ancient surface from the searing heat. Moving outward from Mercury, we encounter Venus. Its perpetual cloud cover traps the radiant energy of the sun within an atmosphere of incredible pressures. From the surface, only a reddish glow reveals the presence of the sun. Beyond Venus, 93 million miles from the sun, is Earth. Its great oceans forming the clouds and air currents which warm and irrigate the planet, shape its continents, and nourish life. Its satellite, the moon, airless, waterless, and scarred by meteors that have bombarded it since the time of its formation, now bears the imprints of our astronauts. A probe of the planet Mars has discovered a dynamic and evolving planet with unexpected geological features. A volcanic mountain, many times larger than the largest volcano on Earth. A vast and deep canyon extending for 2,500 miles. And dry, river-like channels that may have been carved by running water. Beyond the orbit of Mars is the belt of asteroids, craggy chunks of rock and metal, some as small as boulders, others hundreds of miles in diameter. About 500 million miles from the sun, we encounter the first of the giant gas planets, Jupiter, the colossus of the solar system, more massive than all the other planets combined. Deep beneath the maelstrom of clouds that band its surface is a primordial atmosphere much like that in which life awakened on Earth millions of years ago. And drifting on its surface is the mysterious red spot, an immense cyclonic storm that has raged for hundreds of years and continues unabated. Radiating more energy than it receives from the sun, and circled by 14 moons, Jupiter is like a miniature solar system. The next largest of the gas planets is Saturn, girded by rings which, as we approach them, resolve into countless particles of frozen debris and ice, each a tiny moon orbiting the massive planet. And as we continue past the frozen worlds of Uranus and Neptune, we arrive at the outermost planet in the solar system, Pluto. It moves in a dim twilight of unimaginable cold. The sun, 4 billion miles away, is only a brilliant light in the night sky. To travel beyond the solar system to the nearest star would require a journey of more than 5 trillion miles. Yet our sun is only one of 100 billion stars, widely separated from one another in time and space, but all bound by gravity, and all revolving around the central core of our galaxy, the Milky Way. Drifting between the stars are vast clouds of gas and dust, the nebulae, made luminous by the radiation of stars within or near them, or darkly obscuring the light of whatever lies behind them. Here, new stars are being born. About a half-century ago, our galaxy was thought to be alone in the universe. We now know it to be one of a local group of about 20 galaxies. And strewn through the vast reaches of space are more than 10 billion galaxies, grouped in clusters as far as our most sensitive instruments can reach. little is known about the evolution of galaxies, and why some are formless or irregular, others elliptical, and still others spiral-shaped. And we know as little about the galactic core and its role in the galaxy's evolution and structure. The problem has become more perplexing by the discovery that some galaxies are in a state of extreme disarray, exploding, ejecting gaseous matter, or interacting with other galaxies. Even more puzzling are quasars, star-like objects, emitting as much energy every second as the sun radiates in some 10 million years. They appear to be among the most remote objects in space. Stars are born, live out their lifespans, and die. The life history of a star is marked by an opposition of two kinds of pressure. One is the pressure created by the energy in the core of the star, pushing the surface outward. The other is the crushing force of gravity pulling the star's surface inward. When these are balanced, a star becomes stable and shines steadily. As hydrogen fuel is depleted, the release of energy is insufficient to withstand the gravitational pressure, and the core collapses. But compression by gravity raises the temperature in the core, and helium ash rekindles the nuclear fires. Vast amounts of energy are released and lift the outer zones against the force of gravity. The star is now a red giant. In the final stage of its evolution, it is the mass of a star that determines its fate. The Sun, a medium-sized star, remains stable for approximately 10 billion years. Then it will expand to 400 times its present diameter. As it expands, it will engulf the inner planets, Mercury, Venus, Earth, and Mars, and create a nebula extending past the outer planets. After millions of years, its reserves of nuclear fuel will be exhausted, its outer layers will have dissipated, and only a white dwarf star remains, no larger than the Earth. Slowly cooling to zero temperature, it will end its life as a black stellar corpse. When a star more massive than the Sun reaches the red giant stage, the collapse of its core raises its temperature billions of degrees and triggers a spectacular detonation. A supernova explosion. At the center of the explosion, a residue of the star is crushed by gravity to a neutron core, only a few miles across, but so dense that 10 billion tons of its matter would fill only a tablespoon. It spins rapidly, generating radio signals in its strong magnetic field. And a radiation beam sweeping past the Earth is observed as a pulse. The star is known as a pulsar. An even stranger end is predicted for very massive stars. According to the laws of gravity as presently understood, nothing can stop its collapse. The star disappears from our universe, leaving a black hole in space. Its presence can be deduced only by its influence on a visible companion star, distorted out of shape by the black hole's gravitational attraction. Gas, pulled off the visible star, circulates about the black hole, and in the dizzying plunge, it emits X-rays which can be detected in space. No light or matter can ever leave the intense gravitational field of this cosmic abyss. The physical laws that govern the conditions within this bizarre object are totally unknown to us. The evolving universe itself must come to an end. If it continues to expand indefinitely, the light of every star will in time be extinguished, and the galaxies will disappear into infinite darkness. But if gravity halts the expansion, the universe will fall back on itself. Galaxies will lose their separate identities. Stars will explode, and the sky will again be ablaze with light. Finally, all matter will be engulfed in a fireball like that from which it emerged. All things on Earth, living and inert, are formed from the elements forged in some distant and unknown star. On Earth, atoms joined together in definite numbers and patterns compose the organic molecules which form living cells. Since the discovery of complex molecules in the chill vacuum of interstellar space, there is reason to believe that among the countless galaxies in the universe, there are stars orbited by planets favorable for the evolution of intelligent life. Is space travel to these planets possible? Time and distance may be insurmountable barriers. The spacecraft Pioneer, now speeding toward the outer planets and beyond, traveling at 35,000 miles an hour, would take almost 80,000 years to reach the nearest star, Alpha Centauri. A spacecraft traveling 2,500 times faster than Pioneer, at 10% the speed of light, would require so great an expenditure of energy that until new sources have been tapped, it must remain an invention of science fiction. A more practical strategy in the search for extraterrestrial life is to tune in on radio signals traveling at the speed of light, beamed perhaps by creatures on the planet of some distant star. Someday, an array of telescopes, earthbound or lifted to the far side of the moon, may hear faint but unmistakably meaningful sounds amidst the din of cosmic radio chatter. That moment will signal a change in the human condition that we cannot foresee or imagine. For man, wrote H.G. Wells, there is no rest and no ending. He must go on, conquest beyond conquest. And when he has conquered all the deeps of space and all the mysteries of time, still, he will be beginning.
Astronaut Rusty Schweickart joined NASA in 1963. He piloted Apollo 9, logging over 241 hours in space. Schweickart tested the life support packs used on the moon during a 46-minute spacewalk. He was backup commander of the first Skylab mission. Schweickart was then named Director of User Affairs at the NASA headquarters. He was responsible for transferring the discoveries in space into applicable uses for science and commerce.
Hello, I'm Rusty Schweickart, Apollo 9 astronaut. Zero gravity, that is weightlessness, is a strange and somewhat mysterious phenomena for humans who were developed here on the surface of the Earth over millions of years. It affects everything that happens in space, from cell division to exercise. To help ordinary people, and especially kids, get a feeling for this strange environment, as well as to investigate the dynamics of ordinary objects, NASA launched TOYS, a collection of instruments very familiar to all. The film you're about to see is narrated mostly by the astronauts who flew this equipment. They explain the feelings of liftoff, the noise, the shuddering, every detail of flight and orbit. You will get the sense of accomplishment as they send 2 communication satellites off to serve the folks back home. You'll go inside their spaceship and watch as they attempt to play with some of the favorite toys of Earth, a yo-yo, paddleball, jacks, and more. It's a slightly comical, yet educational example of the effects of zero gravity. And you'll hear them talk about re-entering the Earth's atmosphere and how beautiful our home planet is from above. Every step in space brings us closer to fully utilizing this domain for human benefit. Many medical and commercial experiments show the promise of zero gravity to enhance life. The personal experience of weightlessness is its endless fascination. The technical challenge is to convert this unique environment into beneficial products and services. Watch and listen with me as the astronauts tell us about the fun they had with toys in space.
The one thing to say is that this crew represents the top of a big apex, a team that did a super job in the 51D mission. Just to make sure everyone knows who's who here, I'm going to start down at the far end. Jake Garn from the U.S. Senate, and you notice I don't call him Senator Garn, he's Jake to us, and he wouldn't have it any other way. Charlie Walker from McDonnell Douglas, payload specialist, and Dave Griggs, one of our MSs, Jeff Hoffman, an MS, Ray Seddon, an MS, erstwhile Don Williams, our PLT, and then our commander, Bo Bobkill, and I'm going to turn it over to Bo right now.
This was our patch. It was the 4th try at a patch since our mission had been changed so many times. Of course, this is always a very exciting time. It's the night before the launch, when everything is rolled out on a pad and ready. And here we are before dawn coming out, Don and myself, Ray and Jeff, Charlie and Dave and Jake. We were all very anxious. Of course, we had a number of delays, but the moment of truth was quickly arriving. We thought we weren't going to fly because of the weather, but they said, let's go. And here you can see the start sequence of the main engine, the hydrogen igniters spewing flame across behind the engines, and then them starting one at a time. Finally, they're up to speed, they're stabilized, and the solid rocket motors ignite. When the solid rocket motors ignite, you know you're on your way. You know where you're going, where they want you to go, and hope they're pointed in the right direction. It rumbles quite a bit while you're coming off of the pad. There's quite a bit of reflection off of the ground and off of the pad. Once you get up above the tower, the roll starts and things calm down a little bit, but there's still quite a bit of rattle and noise as you're going up through the atmosphere. You have to remember, when you go through 19,000 feet, you're already doing Mach 1. We went to the clouds about 10 or 12,000 feet. We didn't see any moisture, which was what caused the delay, but it was a solid cloud up to about 33 or 34,000 feet. Once we got off of the solid rocket motors, things smoothed down as we were on the main engines, and it was a smooth ride up from there on into orbit. Of course, once we got into orbit, we had the direct insertion, so we didn't do an OMS 1 for quite some time. We were able to see the tank and see it spinning off a mile or so from us. Let me turn it off to Jeff here.
The mission started normally enough with PAM deployment. We've deployed a lot of PAMs in the shuttle program, but it was sure exciting deploying our own. It's a beautiful sight watching it come across right on the Earth's horizon. It's, of course, spinning for gyroscopic stability. and it's just a beautiful sight as it slowly drifts away from us out over the horizon. And you can see the solid rocket motor underneath it, which ignited 45 minutes after deployment and raised the apogee to 22,000 miles, and that satellite's now successfully in geosynchronous orbit. Our second satellite, again, started out normally enough. It's the SYNCOM, the third one that NASA has launched. It's a lovely sight seeing it come out sideways like this sort of Frisbee deployment. You see that white antenna on the top. That's the omnidirectional antenna, which we expected to see come to a standing position about 1 minute and 20 seconds after the deployment. That's certainly the way it always happened in the simulator, but SimSoup had another idea this time, and well, after about 2 minutes, it finally sunk into us that it wasn't going to move, and of course we gave the call down to the ground. We then followed it. The other thing that should happen is that the satellite should spin up from its 2 RPM motion. After we deploy, then we burn our own engines, and from the 0G, the 1/10 of a G acceleration really gets your attention. Here's the ohms cutoff, and you can see all of the flaming coming around. I'm going to turn it over to Jake Garn now.
Now we're simply drifting away from the satellite. This is Ray doing her echo sounding, taking her blood pressure at this point while being restrained to the locker so she doesn't float off to some faraway place. And this is simply me, guinea pig, barfing Jake Garn with a few electrodes. I just want you to note that I was a perfect subject for the electroencephalogram, the top of my head. If I'd had hair, I couldn't have accomplished that particular task. And that amplifier floating there was no problem whatsoever. Here's Ray.
This is the American flight echocardiograph put together by some of our fine folks here at JSC. First American echo done in space. The transducer that I've got on my chest emits sound waves that are reflected back into the transducer, and they generate a two-dimensional picture of my heart on the screen. The system worked very well, and we got some excellent pictures of the heart. Here is a picture of my heart. The little flapping thing in the middle is the mitral valve on the left side of my heart, and my heart chamber is pumping blood, and we were looking at volume changes in the heart and differences in resistance in the peripheral blood vessels.
Here's some scenes from the operation of the electrophoresis equipment on board. In addition to letting the machine do its thing, which it did very well this time, I conducted some tests on samples of fluid from the device. And here I'm transferring some fluid from container to container and finally to a sample tray where I could read the results. The operations sometimes are a little hard when you've got to use both hands and you've got no feet on the floor. But the operations went well. The device and the tests all worked very well. As a matter of fact, we had the electrophoresis equipment operated as a clean machine this time, both electromechanically and biologically. I even performed some standard operations in calibrating flow rates through the machine at the sample pump, which you see me doing here. You know, just a normal orientation for these kinds of operations.
Well, it's constantly fascinating just to watch the way objects behave in zero gravity. Here we have a set of gyro-stabilized binoculars. There was a little bit too much friction in them, so they were actually a bit gyro-unstabilized. But still, with 14-power binoculars, it was just amazing what we could see on the ground. And, of course, I also enjoyed what I could see up in the sky since I'm an astronomer. We also carried some science demonstration objects, commonly known as TOYS. This was done primarily to make some educational footage, which we can use and distribute to science teachers throughout the country. Here, Bo forgot to spin the gyroscope up, and somehow it just didn't stay stable. So we're going to give him another chance, and here he's going to get it spinning. There we go. Of course, the principle of gyroscopic stability has been around a long time. We use it for navigation. Our satellites use it when they come out of the cargo bay. But of course, without gravity and just being able to float it free here, you can study the behavior of the gyroscope and watch the way it moves around in a way that we never get a chance to do in laboratories on the Earth. I'm sure all of you have held a gyroscope on a string or on your fingers, and after a while, as it spins down, the force of gravity starts to torque it and it starts to precess around. Of course, that never happens in zero gravity. You can keep playing with it almost up to the moment where it is not spinning at all, and it still stays stable. In fact, it was just a constant source of fascination, all the different things you could do with these very ordinary devices. This is a little magnetic wheelo that I'm using. Normally on the Earth you start this with gravity. I found it was pretty easy to start it up using centrifugal force. This one, as long as I was holding it, behaved pretty much the way it did on the Earth. But as soon as you let it go, then it does all sorts of neat things. And here comes Mr. Yo-Yo. I've had a lot of discussions with physicist friends of mine about whether the yo-yo was going to work, and it worked fabulous. You could do it fast, you could do it slow, you could do it to the ceiling. That's the famous oi-oi. Dave did flying saucers around the moon. He's a real champ, and if they don't let him into the Yo-Yo Association of America, there's just no justice in the world. Putting the jacks here, there was constant danger of massive explosions if the ball came back in the wrong place. We managed to go through without ever losing the jacks, and although it's not on film, Ray did manage to do her 12sies by the end of the flight. If you let a paper airplane just float, it's pretty much carried away by the air currents in the shuttle, as you see here. And so it really doesn't take very much force just to start it on the most beautiful flight that you've ever seen of any paper glider.
Hope you like our home movies so far. The paddleball behaved a lot like it does on Earth in that you can paddle it in nearly any direction if you're clever enough. I'm not sure I am clever enough to keep it going in each direction. And as you can see here, so the ins and outs, ups and downs were about the same. It's a little harder to do, to do this trick on Earth. The straightforward sort of paddleball operation is much slower, and it's much easier. This one is a little tougher. Jeff has here some magnetic marbles. I'm not sure how you shoot marbles in space because it's a little hard to keep them in that ring. But your shooter seems to work fine. It joins right up with them all, and it forms into a toroid, as you might expect, with the magnetic lines and the magnetism that's inherent in the marbles. If you watch carefully now, on not this one, but the one after this, as Jeff sails the marble past after he repositions his ring here with its little tail, and relative to the horizontal lines on the bulkhead behind him, watch what this marble does. See it curve upward as the magnetic lines of force pass by the others. And here's our unofficial mascot. You might say he flipped out over this. Rat stuff really had it. The slinky, without the sag that you have to contend with in 1G, behaved pretty much the same as it does in 1G. You can start to see that, of course, they've set up a sine wave oscillation here, which continues to be reflected back and forth, and now a double one or perhaps a triple, and perhaps within there you can also see the standing waves reflected back and forth. The centrifugal force, of course, keeps this little car going around its track. On Earth, when it gets to the top, it would, of course, fall out. In space, what do you expect it's going to do? Well, with a little help from the doctor, sure enough, it falls out.
This is fly swatter ops. The ground had decided at this point in time that we were going to re-rendezvous with CENTCOM and attempt to activate the separation switch with some of our homemade devices. This is the one that we call the fly swatter. It was made from a metallic swizzle stick reach mechanism that we had on board and some plastic book covers and gray tape. The ground gave us specific instructions on how to build it, what size it should be, and here Jake is helping me put some stitching into it to hold it together. The other one was called the lacrosse stick. It was a different sort of device.
Here we are on day 5, the regular day of our entry, had we maintained our normal activity plan.
You can't put your pants on 2 legs at a time.
That's Jeff putting on a lower torso assembly. It's a rather cumbersome task to get yourself suited up. EVA activity is a rather messy task to begin with. It really ties up the mid-deck. You can see all the different pieces of equipment we have laying around. Back in the background there is Charlie Cephas Walker giving Jeff a hand. We had reduced the cabin pressure down to 10.2 at this point. We did that on day 4 to denitrogenate Jeff's and my blood. Here we are with our lacrosse stick and the fly swatter. We kept close grasps on those because we certainly needed them to do the activity we intended to do later on. Didn't want to leave them outside the airlock when we depressed. There's Bo assisting me getting suited up there, getting the lower torso assembly attached to the hard upper torso. And here's Jeff popping up into the hard upper torso. Very crowded in the airlock. It's a small airlock. You can see me hanging on the right and Bo ricocheting back and forth between both Jeff and myself. Here we are shortly before fastening the upper torso to the lower torso assembly. We're hanging there making some last-minute adjustments. Ray's getting our picture. We're close to the point where we're going to be closing up the airlock and saying goodbye to the rest of the crew. Fully suited now, making some last-minute adjustments on gloves, glove fit, making sure that we have all the equipment that's required for the EVA. And momentarily we're going to be outside after we depress for the airlock down to 0 and open up the outer hatch. Ray had precisely positioned the remote manipulating system and its end effector right along the starboard longeron there. Convenient place. Jeff was able to tether himself on the outboard side to give himself some stability for work, and I had tethered myself on the inboard side, and each of us 180 degrees apart started the work of putting the 2 devices, the lacrosse stick and the fly swatter, affixing them to the end effector. Here's a view from the C camera. In the very near foreground you can see the lacrosse stick still tethered to the longeron, and what we're working on right now is actually putting the fly swatter in at the 12 o'clock position with respect to the end effector. We tighten the 2 devices down with a device that's most familiar to folks here on here on Earth is more like a come-along device.
You can see me moving it up and down there to actually take up the slack of the system.
The total EVA ran about 3 hours and 6 minutes and a few seconds. Most of the work activity of putting the 2 devices onto the end effector was accomplished within the first hour, slightly over an hour. We then, at the completion of that, had to move the arm over back to its manipulating position mechanisms, place the arm back down into those mechanisms, and roll the arm inboard as if we were going to stow and make a re-entry. The purpose for that being that we weren't really sure whether the fly swatter or the lacrosse stick might impinge upon the doors and prevent them being closed. We did roll the arm in afterwards, check the clearance, and there was some interference between the lacrosse stick and one of the cameras, but the interference was slight, and we had no problems with interference with the doors and the potential for not being able to close the doors for entry. Another view from the C camera, you can see now that we've got the fly swatter on at the 12 o'clock position, and we're getting the lacrosse stick fixed in at the 9 o'clock position from Yearville Point. Jeff, you want to say a couple of words here, maybe?
Well, we did all of our actual work during the day because Houston wanted to be able to see what we were doing. If you heard the conversations, you'll realize that we certainly were not on our own out there. We were talking very closely with people inside the cabin and with the people on the ground, and it was a massive effort that went into doing this. It did mean, of course, that when we went past the Terminator and it got dark in the bay, the ground just asked us to just sort of hang on and, well, watch the world go by. And I think those were some of the most memorable moments of my life. The feeling when you're just hanging on to the side of the orbiter, not working too hard, not exerting any force. I felt myself almost decoupled from the spaceship and became for a few really beautiful moments just a human satellite floating around.
Here's Ray back inside, repositioning the arm and the finale. It's a beautiful shot of Jeff working himself forward on the starboard longeron. I'm concurrently working myself forward on the port. At the end of the EVA, we're back to putting our tools back into the chest that we have out in the payload bay for them, and re-entering the airlock. And from that point, we've done everything we can, and we turn it back over to Don and Bo, who are going to affect the rendezvous.
Now we had to go to work with the rendezvous targeting, none of which we had on board. As far as the procedures, the flight data file and the inputs we need to do this, so we all came up by teleprinter, perhaps one of the longest teleprinter messages in the space program. But we made ourselves a book and with a little Scotch tape and a lot of cutting and pasting, and got the rendezvous procedures together. This is a camera zoom in on the SYNCOM as we were approaching it from underneath and coming up onto the velocity vector of the satellite. You can see it rotating here at about 2 RPM. You're looking at the bottom end of it. After we're established into a tracking position, Bo moved back to the aft station where he's standing on a starboard side now and flying the spacecraft from there. And that's where all rendezvous and proximity ops are flown in the spacecraft, generally standing in the back, hovering in the back, if you will, looking out through the overhead window using the hand controllers, the rotational and translational hand controllers that are in the back of the spacecraft. As it comes around here, we'll be able to show you this arming lever before we took a swat at it. Bo is looking. Here it comes now in that orange rectangle in the lower right-hand corner of it. You see what the lever looked like when we first saw it. And then Ray got ready to take a swipe at it.
I guess there was some question about whether the arm could be used in this manner with some rather primitive tools on the end of it to hit that lever and see if we could activate the separation switches by it. If you'll watch the lacrosse stick on this first pass, you'll see it come in, and I'll get your opinion on whether you think we got it or not. Here it comes in, grabbed it, pulled it. Real good pull first time, went in with a fly swatter the second time, tried to hook it on one of the rungs of the ladder. Here we come again, grabbed it. That's number 2. This time we try and hit it with the base of the cone, which is a more solid object. Get it one more time. That's 3. We got, as we can count, at least 3 really good whacks at it. At this point in time, the window closed that we were supposed to be hitting this thing, and since we had made hard contact with it, we had to back off from it at this point in case it was going to activate itself sometime later.
Bo flew the initial SEP burn from the back, which was in a Z orbiter direction. And meanwhile, while he was doing that, I was targeting up a small out-of-plane burn to get us out of the plane of the spacecraft so we wouldn't come close to it on subsequent revolutions. And then 15 minutes later, we targeted an Ohms burn to do the final separation. The reentry was a very exciting part of the flight for me, at least, because in a lot of it we were in this particular attitude, and I got to look out the window and see the ground going by. It goes by a lot faster when you're down below than it does up at orbital velocity. We rolled out coming over the central part of Florida here and into the Kennedy Space Center into a slight left bank prior to intercepting the heading alignment circle. We had gone just a little north of ground track, had corrected, and then come back to our nominal ground track. You can see the speed brake opening here to control the energy and rate of descent of the spacecraft. And of course, we're a glider here at slightly under 200,000 pounds, as on all previous flights. It's a beautiful day in Florida. The sun was shining. There were a few scattered clouds down over Melbourne. Kennedy Space Center itself was clear. I had a great view as we came around the heading alignment turn on the final for runway 33 at the Cape. I was talking to Bo all the way around the turn relative to lineup and glide slope and energy management, and he was doing a great job of flying the airplane right around there. As we roll out on final here, I'll let him describe the landing.
As you know, we were waved off once. We didn't think we were coming in because seldom does the weather get better in Florida when it's cloudy in the morning, but it did. It was beautiful. Here we're coming right down near the runway and started our pull-out for the final landing. Here we're coming over the Banana Creek, and in just a second you'll see the gear come down, and finally the overrun of the runway come up. There was a right crosswind. We touched down just a little bit to the left of the center line and drifted a little bit farther to the left with the crosswind.
I put in a correction and brought it back to the center line. It handled beautifully. We rolled out with just moderate braking and stopped with about 3,000 feet to go. We probably could have stopped a lot shorter if I had used a lot harder braking. At that point, we were all elated. We felt that we were really home. I mean, we had gone through this mission. We had done all of these things. Here we were rolling out. It was certainly under control. We were ready to stop and see our families and come home. What else could possibly go wrong? We, a few seconds later, felt one of the wheel brakes lock up, and it was no problem to control the vehicle. I mean, it was absolutely under control. There was no question about it, and you can see that. It didn't diverge at all. And then just about the time we came to a stop, the right tire blew. I think you'll see when we come down the ladders that there are broad smiles on everyone's face. And it was a demanding, challenging, extremely exciting, and of course, space flight is always beautiful. We're all looking forward to our next flight. Quite a few of us have them assigned right now, and we can't hardly wait.